API Secure, we will continue to talk in the solution track about like what are the current tooling, solutions, and vendor that exist to actually solve the API security problem and challenge. And for that, we will have for now our next speakers, who is Joshua Behar from L7 Defense, who is a cybersecurity expert, and who will talk with us about the illusion of proactive code hardening against business logic attacks, myth versus reality. Hello, Joshua. How are you?
Hello. Thank you for hosting us. Can you hear me well?
Really well. Are you able to share your slides with us?
Yes. You can't see them right now?
That's perfect. That's full screen. That's awesome.
Okay, perfect. All right. Should I start?
Yeah, you can start right now.
Okay, perfect. So thank you again. So welcome to our presentation, The Illusion of Proactive Code Hardening Against Business Logic Attacks, Myth versus Reality. Or in other words, can business logic vulnerabilities be protected by design? So business logic attacks are a fascinating topic in my eyes, as it tries to bypass the legitimate flows, arguments, and structure versus the more common attacks that go after broken or missing security controls. So in the next 20 minutes or so, I will explore what is business logic attacks and the possible ways to secure against them by design. My name is Joshua Behar. My email is listed here on the first slide and on the last slide. And you're welcome to email me with any additional questions or comments you might have. Let's try to move forward here. Okay, so during this presentation, I will cover two main questions. First, starting with what are business logic type attacks? And the second question is, can it be prevented by design at what cost? So what are business logic attacks? So in my definition, business logic attacks try to bypass their legitimate flows, function, arguments, and structure. And in order to make it easier to understand, I really group the business logic type attacks into four main areas. And let's look at the four areas. And the first one is really around transaction flow manipulation. The area two is a shadow API endpoint manipulation. The third one is the API endpoint argument tempering. And the fourth one is API endpoint structural tempering. So in the next few slides, we will look into each one of those BL areas, and we'll try to answer the question on the proper design, and it can prevent this type of attack. All right. So let's start with transactional flow manipulation. So the hacker can try to skip steps, add steps, or temper steps in order to temper the flow. So let's take an example here. And you can see here, this table on the right, I was trying to simplify what we are seeing here. So we have here a website that is offering 20 different transactions. Now imagine that each transaction includes 3 steps, which is quite common. Each step is made by a single API endpoint or URL request. And as you can tell from just looking at the table on the right, there are many available paths just from this simple scenario. And later on, we're going to see even more complex scenarios. So what is the myth in this industry is that I name it a myth, as it is common misconception in the industry where people believe that as each transaction is unique, it can be protected by design, for example, by whitelisting the unique endpoint predecessor. The reality is that whitelisting each endpoint predecessor might be done only in theory. If you invest a lot of money and effort to keep and then redoing it all over time, every time that an API endpoint is changing. So let's look at the second example. Second example is actually looking at Shadow API endpoint. The definition is that Shadow API are a category of backend APIs, often hidden from the views of traditional security tools and API gateways. These undiscovered APIs often run on Informatical infrastructure in the public cloud. So let's look at specific manipulation. The first one is calling an unauthorized function. The second one is calling with unauthorized methods. So let's look an example here. So we have here several tempering options is listed here. So an open source based solution with the user and admin API endpoints. And the attack method here that I'm listing on the shadow endpoint is accessing forbidden functionality and or using unauthorized method. So what will be the typical protected by design is setting rules to the full metrics. If you look here at number of function, number of users, number of methods, and then applying or coding API endpoint governance or specific standard for that. So once again, this is pretty costly and error-prone process to set and to maintain at the real-world scenario. Let's move to the third one. And the third one is an endpoint argument tempering. So in this case, you can see here that the attacker changed the values to an API. Some of the tempering will be here, whether a wild argument, you're trying to use a wild argument value, trying to use an out of range value, mistype values, or unconventional inputs. If you look here to the right, I drew here an example. You can see here, instead of using 126, is actually trying to use 123, is trying to use different argument out of range sometimes, or trying to do all sorts of other inputs here. So the example that we have here, you just imagine again using an open source based solution with thousands of arguments. Some of them has the same, I'll share the same dependencies. And the attack method here is using randomly tempering arguments. And the protection by design is really trying to mask and whitelist arguments value by using explicit code. So once again, if you try to look at all these different options that is in front of you, you can understand that this can be very costly and error-prone process to set and maintain such elements. Let's look at the fourth one, and this is an 8-point structural tempering. So in this case, you're trying to either try to temper with missing arguments or adding additional arguments, or actually looking at disorder, trying to disorder arguments. And you can see here this drawing on the right, where I was trying to show a different structural tempering options. So the main challenge that we have is that in most medium-sized or even large organization, you will see thousands of API endpoints that are continuously being developed, especially now if you look at agile type development where the change is quite rapid. And the attack method here is by accessing randomly API's endpoint until an unprotected structure is found. And then, of course, you can try to apply the different tempering methods. So what will be the protection by design is, for example, using coding validation to the functional interface. And also here on the fourth methods, it can be pretty costly and error-prone process to set and maintain this type of protection. So what we've seen in the last several slides, we actually saw that there is quite a large attack surface on the BL type attacks. Starting with the first one, we looked at transactional flow manipulation. And here, the way to protect by design is by setting rules to each endpoint, and to by whitelisting APIs endpoint unique predecessor. So that was the first thing that we cover. The second thing that we cover actually API endpoint argument tempering. And once again, the way to protect by design is by setting rules to each argument, trying to mask and whitelisting the argument's value. So that will be the second method. The third one is by looking at the shadow API endpoint manipulation. And once again, there's a lot of work here in setting rules to each endpoint. And then, as I mentioned, it's the function, multiply user, multiply the different methods. And the last one, or the fourth one, was API endpoint structural tempering. And once again, the protection by design here is by setting rules to each endpoint and adding validation rules to each functional interface. So if you take this attack surface, sorry, and you just do the math, you multiply the number of variants and the number of activities that you need to do by type of possible attacks or manipulation, by the number of different options, you actually can see that that can be a pretty costly and error-prone process, not just a one-time setup, but actually to maintain it in real-world systems. So let's take an example here. And in this case, I looked at ebay.com, and I did a simple search. And you can see here, I'm going to search for a Sony camera. And you just put here in the search bar, I'm looking for a Sony camera. The interesting part, if you click on the view source, you can see immediately, and here I know this is an eyesore, you can see right here as an example of an API endpoint in the URL for a server or for service. And if I will scroll down throughout this list, you will see that this is not the only one. There will be quite a lot of other API endpoints which are listing here. So everything here is operating to a response and request. And this is the initial attack surface that from my first page going into eBay. Let's continue. So you can see here, this is my Sony camera search. And you can see the minute that I click enter and I'm starting the search, automatically I'm being presented by three different options. The first one, do you want to see all listing? You can see it here. Do you want to actually go into an auction, or do you want to go into buy it now? So that's the response that I received. And let's say that I'm clicking next, and you can see here the Sony a6000 camera kit. By the way, a very good camera to use. It's a mirrorless camera. So you can see here I'm getting two different options here in the tree. The first one, see similar products. Here, this is a similar product. The second thing is, do you want to place a bid, or do you want to add it to a watch list? Again, three different options. If I decided to move forward, you can see it here. It's giving me the option now to either buy it now, you can add it to a cart, or you can add it to a watch list. So again, you can see the tree is evolving as we move along. The next thing, if I click next, it will be sign in to checkout or checkout as a guest. And of course, you get here, if you click on the sign in, I have quite a lot of options how to sign in, whether an email, with Facebook, with Google, with Apple. So what we've seen here, and I'm not listing all the different options, we started by searching a product. You saw that that I got a response of all listing, auction, buy it now. And for each one of these three branches here, I've got different options. This is my request. This is the response. Select the product, see similar products, buy it now, view in cards. And again, and at a certain point, I stopped drawing the tree because it was becoming too complex. So every page here contains more than a single API endpoint, and the complexity here is quite huge. So that's an example of a very, very wide system to protect. So just imagine doing the effort to do it by design. So maybe a few conclusions of what I presented in this presentation. Conclusion number one is each attack type is independent of the other types, resulting in an enormous attack surface that cannot be protected by design at a reasonable cost. I think that's the first thing that we saw. Different attacks, each one is independent. The second thing is the attack surface is huge. So at any given time or any given round of testing, a significant amount of evidence will be found of undetected logical vulnerabilities, and then potentially leading application owners that their application was sufficiently tested. And we all know, the friction between the DevOps and the SecOps regarding testing and validating each one of these APIs. The next conclusion, or conclusion three, it is clear from the previous point that it's impossible and inefficient to try and fix vulnerabilities by design. And I use the analogy, it's like trying to dry the sea with a spoon because of the complexity and the enormous attack surface here. So maybe my last slide here is really speaking about the common misconception that business logic vulnerabilities are flaws in the design and implementation of an application that allows an attacker to elicit unintended behavior. And I believe that due to the enormous and ever-changing attack surface, it is impossible to protect by design. So a better way to protect a BL-type attacks is a must. So that's the main key message that I wanted to deliver today. And at this point, I would like to open the discussion for questions and answers.
Yeah, thank you very much, Joshua. One question about, when you say it's really hard to secure the business logic, but yeah, on the practice side, how it can be solved working with engineers or working with testers, or how it can be solved on the, let's say, the the way to work with others, like, the team side, team collaboration.
Right. So I think the key message here is the word that changed. The level of complexity went high, really high. And as a result, you cannot focus on manual work anymore. And you need to be much faster and much agile. Like we see is that more and more of the attacks is based on AI type of attacks. So it means that you need to harvest technology, you need to harvest automation, and without pitching L7 defense, that's some of the things you need to bring automatic tools in collaboration with very smart artificial intelligence and machine learning in order to automate this process, and not trying to rely on the old way of doing security is by trying to do or to utilize by design methods and really hoping that you can provide an efficient protection.
So we have a question about, like, can you explain what happens in the mind of an attacker when he tries to find business logic vulnerabilities?
I think overall, when he looks especially on a complex system, he almost knows for sure that he will find a hole, because as an attacker, you only need to find one way to penetrate the organization, and once you're in, or once you are inside, then you start moving laterally. So I think that we, from the protection side, have a huge job. We need to protect a very large attack surface, which is very complex. The hacker, from his perspective, only need to find a very one specific way to get in, and from there, his life is much easier.
Yeah. Is it the price to pay, the reward of, like, full automation and large platformization of businesses to have more flows, especially on the business logic side? Like, will we solve it at some point?
I'm not sure that I follow this question. Can you repeat the question?
The question is like, is it the price to pay, in a sense, to have larger platforms, more automation, more complex systems, and so at the end having more business logic, let's say, surface attack?
I think the expectation from consumers today is that you're going to offer them a more sophisticated systems. You cannot stay back and says, I'm not going to provide a cutting edge system just because I'm more exposed. It just means that you need to up your security. So like you're investing in new systems, in new technology, you need to find ways to improve your security. Just think about the autonomous car. Just because there is there's exposure on autonomous cars and there is potential danger, it does not mean that we're not going to move into autonomous cars. We just mean that we need to learn the business and we need to find ways to protect the cars in a more efficient ways. And I can tell you that it's not just L7. I'm sure that there's other good people out there that are investing time and effort into this next generation technologies and harvesting the best technologies out there to provide this next generation protection.
Yeah, we have a question from John Shimshak. What are your suggestions to stop business logic attacks?
Okay. I can tell you overall in the industry, there are very few companies today that's offering business logic attacks, automatic, not code base or by design solutions. We are one of them. And if shoot me an email. I would love to share with you what we do and how we actually protect business logic attacks. I can tell you that we are in production with customers with the business logic system. And up till now, we've seen some very impressive results. So just talk to me and I would love to share more in depth about how it works and why we believe that this is the right way to move forward.
Do you include also, let's say, a protection against social engineering when you try to also do a business logic defense?
We are trying to, of course, to look at all different angles because one of the things that when we analyze a situation, we look not just at the business logic type of attacks. And originally we started with the OWASP 10, and we realized that the OWASP 10 did not cover the business logic type attacks to its fullest, and that's one of the reasons that we expanded beyond the the OWASP 10 in order to make sure that we are covering many other attacks and not just business logic others. The Log4j was a good example. We did not anticipate the Log4j, and we were able to catch it without making changes to our systems.
Yeah, thank you very much, Joshua, for explaining that. Yeah, security is a multi-layer, multi-depth, multi-factor. But yeah, thank you for pointing that the business logic point that is not enough addressed, even in security conferences. Thank you very much, Joshua. And
Thank you very
now
much.